In the last lecture, we were discussing dimensional analysis. After deriving the dimensions of various quantities using relations that involve those quantities, mechanical quantities, thermal quantities, electrical quantities, we had come down to dimensional analysis and the Buckingham Pi theorem. The Buckingham Pi theorem states that if there are n dimensional quantities and f m fundamental dimensions, then there will be a total of n minus m dimensionless groups that characterize the system. That is, we do not have to solve or we do not have to obtain results for variations in all n dimensional quantities. It is sufficient to obtain results for variation in the n minus m dimensionless groups. We had applied this to the problem of a sphere settling in a fluid. The conservation equation, the momentum balance equation for the sphere, acceleration times mass on the left side, on the right side are the forces. mg is the gravitational force, Fb is the buoyancy force, and Fd is what is called the fluid drag force. This fluid drag force is due to the flow of the fluid around the particle. As the particle moves downwards, the fluid has to flow around the particle. It is displaced out from the upstream side and back in on the downstream side. And this fluid flow generates stresses, and therefore, there is dissipation of energy due to fluid viscosity. This frictional effect causes a drag force on the fluid, and our objective was to find out what is this drag force, what does it depend upon. So, in any problem you have one dependent group and a set of n minus 1 independent groups. The independent groups are what are specified, and the dependent quantity is what you want to determine. In our case, the dependent quantity was the drag force Fd with dimensions of force, mass times acceleration. The independent quantities are those that affect the drag force. The diameter obviously affects the drag force, because as the diameter changes, the force will also change. The velocity, a faster moving fluid particle, you would expect to exert a higher drag force. And then there are the fluid properties, the density and the viscosity. So, we had 4 independent dimensionless groups and 1 dependent dimensionless group. That means that we have one dependent dimension, we had 4 independent dimensional parameters and 1 dependent dimensional parameter. That means that we have a total of 5, and they involve 3 dimensions: mass, length and time. Therefore, there are a total of n minus m. N is 5, m is 3, n minus m is 2 dimensionless groups. One of them is independent and the other is dependent. So, we had calculated the drag force by scaling it with the viscosity. I told you can scale it either with the viscosity or the density, because there has to be the mass dimension in this dimensionless group. Okay. So, we had scaled this by the viscosity, and based upon that we had got a dimensionless group, okay, which is the force divided by mu v times d. The independent parameter, once again we had set the exponent of the density equal to 1 and calculated the exponents of the other quantities, and we had got the Reynolds number, rho v d by mu, ratio of inertial and viscous forces. Okay. So, that is the 2 groups. So, therefore, the drag force, the scaled drag force here is a function of the Reynolds number. And we could get simplifications in different limits. In the limit where the Reynolds number is very small, you would expect inertial effects to not be important. The density is no longer a parameter, okay, and therefore, the density is no longer a parameter, and therefore, the drag force has to depend upon the viscosity alone. And in that case, there is only one possible dependence, and that is for this f d v star to be a constant. Okay. That is, the drag force divided by mu d v is a constant. We cannot determine the constant from dimensional analysis, but more detailed calculations will show that this constant is equal to 3 times pi. So, just on dimensional analysis, we managed to get the drag force to within a proportionality constant in the limit of low Reynolds number. At high Reynolds number, viscous forces are not important, and if viscosity is no longer a parameter, then you define the inertial scaled drag force based upon the inertial scaling rho v square d square, and this thing is just equal to the viscous drag force times the Reynolds number inverse. Okay. I told you that the dimensionless group that is actually used in calculations is what is called the drag coefficient. This drag coefficient, you take the drag force divided by the projected area of the sphere perpendicular to the surface. Okay. Drag force times the projected area is approximately equal to the difference in pressure between the upstream and the downstream sides. Divide that by the kinetic energy per unit volume, okay, and that is defined as the drag coefficient. It is within a proportionality constant just equal to the inertial scaling of the drag force, okay, within a proportionality constant. Okay. So, let us use the Buckingham Pi theorem for some other problems. Okay. So, one of the problems that I will use is for what is called Brownian diffusion. Okay. Very small particles of the size of approximately a micron or so, both in water and in air, they execute a random fluctuating motion called a Brownian motion. Okay. So, these are called colloidal particles, and if you have a colloidal particle at some location, okay, this particle, if you watch it in time, it will undergo some kind of a random motion called a Brownian motion. This Brownian motion has no preferred direction. It has equal probability of going in all directions. Okay. But however, if you look at any instant of time and ask what is the probability of finding the particle at some location from the initial distance, okay. If for example, I put an axis here, okay, x and y, okay, and if I ask as a function of time as this particle moves around, okay, how does the average value of x, okay, vary with time? This is equal to 0 because it has equal probability of going either to the left or the right. Okay. So, therefore, if I plot the x position of the particle as a function of time, I will get something that is fluctuating in time, and if I average this out, I will get 0. Okay. So, the average x location is equal to 0. Similarly, the y position is also 0 on average. Okay. However, x square, okay, this is not equal to 0 because even though x can be positive or negative, x square always has to be positive. Okay. And therefore, if I take the square of this, I will get something that is always positive. Okay, it will go through 0 wherever x goes through 0, but it is always positive. Okay. So, the average of this is non-zero. Okay. And similarly, if I take just the distance from the origin as r, okay, the distance from the origin as r, okay, in a 2 or a 3 dimensional coordinate system, this average of r square is not equal to 0. Okay. In contrast, it increases linearly with time. Okay. So, if I plot for example, okay, r square average versus time, okay, this is something that will increase linearly in time. Okay. And the Brownian diffusion coefficient is defined as the Brownian diffusion coefficient is equal to r square, okay, by 2 nd Brownian diffusive 2 nd times t. Okay. R square by t is the slope of this, and I divide that by 2 times nd, where n is the dimension. Okay. So, if I am looking at a particle moving in just one dimension, going back and forth left to right, okay, nd is 1, and r square by 2 dt is equal to the Brownian diffusion coefficient. If I am looking at a particle moving in a plane, okay, it is confined to 2 dimensions, and nd is equal to 2, and r square by 4 dt is the Brownian diffusion coefficient, and in 3 dimensions is equal to r square by 6 dt. Okay. So, this is equal to, so let me just write that down, where r is the displacement from the initial location. Okay, r is the displacement from the initial location. 2. Okay. So, that is the Brownian diffusion coefficient, that is the definition. Okay. Now, how do we estimate this Brownian diffusion coefficient? Okay. So, for that we have to look at the physics of why Brownian diffusion takes place. Okay. If I have a colloidal particle, okay, a micron or so, in a solvent whose molecules are much smaller, okay, for example, for liquids like water and so on, the size of the molecules is of the order of angstroms, 10 power minus 10 meters. The size of a colloidal particle is a micron or so, 10 power minus 6 meters. So, the particle is much larger than the molecules. And in a liquid or even in a gas, all molecules have fluctuating motion, okay, which is given by the equipartition of energy, half m v square is equal to 3 by 2 kb T, where kb is the Boltzmann constant and T is the temperature. So, these molecules are constantly colliding with this larger particle. Okay. The molecules in the liquid are constantly colliding with the larger particle. On average, the total impulse in any direction is 0, because there is equal probability of molecules colliding on the right as on the left. Okay. However, instantaneously there could be an asymmetry in the impulse on a particle, okay, and it is this asymmetry that causes the particle to execute Brownian motion. If the particle is very large, then the asymmetry is very less, and therefore you do not see it move. Okay. Whereas, when a particle is sufficiently small, there is a discernible asymmetry in the impulse exerted on the particle by the molecules, and you will see the Brownian motion of the particle. Okay. So, that is the physics behind Brownian motion. So, the Brownian motion obviously has to depend upon kBt. Okay. The Brownian motion, the Brownian diffusion coefficient has to obviously depend upon kBt. As you increase the temperature, the molecular fluctuating velocity increases, therefore, the Brownian diffusivity also you would expect to increase. What are the other things that affect this Brownian motion? Okay. One thing is, of course, the viscous drag on the particle, which tends to resist the Brownian motion. Recall that when we did the particle settling in a fluid, I said that at low Reynolds number the force is entirely viscous. These are very small particles of the order of microns in size, and therefore, you would expect the force to be entirely viscous. Therefore, the fluid density will not affect the drag force, it is only the viscosity that will affect the drag force. Okay. So, therefore, the independent dimensionless group, the dependent dimensional parameter is dB, okay, and dB as I defined it was equal to a length square divided by time. Okay. dB as I have defined it, nd is the number of dimensions, so that is dimensionless, that is equal to length square divided by time. Okay. So, the dimension of this is L square T inverse. That is why it is called diffusion coefficient. It has the same dimension as the mass diffusion coefficient, length square per unit time, that we had seen earlier. Okay. So, this is a dependent dimensionless parameter, and the independent parameters. Okay. First thing I said was the temperature, okay, the temperature with theta, okay, the temperature with theta as the dimension. Okay, note that theta is being used for the temperature. Okay, so let me just note that here. And then there is the Boltzmann constant. Kb. Okay. Kb times T is a energy. Okay. Kb times T is an energy. So, therefore, Kb has dimensions of energy per unit temperature. Energy is m L square T power minus 2, force into distance, force is mass times acceleration, and I have to divide it by temperature to get a dimension of energy. Okay. Then I have the diameter of the particle d with units of length, and I also have the viscosity, because I told you that the drag force that is resisting, okay, the drag force that is resisting the particle motion is primarily viscous, because for these very small particles the Reynolds number rho v d by mu is very small, because the diameter is very small. Therefore, viscosity is the other parameter. This has dimensions of m L inverse T inverse. Okay. So, I have 1 dependent and 4 independent parameters, total 5. I have 4 dimensions, mass, length, time and temperature. There is only one dimensionless group. Okay. That dimensionless group can be taken as, I can always take the independent parameter to the first power, the dependent parameter to the first power, times combinations of the independent parameter, Kb per alpha, T per beta, okay, d per gamma and mu per delta. Okay. And I substitute the dimensions. On the left is a dimensionless group, okay, m per 0, L per 0, T per 0, theta per 0 is equal to L square T inverse into m L square T power minus 2 theta inverse per alpha, okay, times theta per beta times L per gamma times m L inverse T inverse whole power delta. Okay. And now I collect all the dimensions, okay, collect all the dimensions. Mass dimension 0 is equal to alpha plus delta. Okay. Length dimension, on the left side I have 0, on the right side I have 2 from the diffusion coefficient, okay, and then I have plus 2 alpha from the Boltzmann constant plus gamma, plus gamma minus delta. Okay. Time dimension 0 on the left, okay, from diffusion coefficient have -1, -2 alpha, okay, minus delta, and the temperature dimension 0 is equal to alpha plus beta. Okay. I am sorry, minus alpha plus beta. Okay. So, from this you can easily see you get alpha is equal to beta is equal to minus delta, okay, from these two equations, okay, and you substitute that into the other equation, and okay, so this equation will become, okay, 2 plus 2 alpha plus gamma plus alpha is equal to 0, and minus 1 minus 2 alpha plus alpha is equal to 0. Okay. And therefore, I will get after solving these two, I will get alpha is equal to -1, right, beta is equal to -1, gamma is equal to 1, and delta is equal to 1. Okay, so, that is the final expression that we get. Therefore, the dimensionless group is phi is equal to dB, okay, into mu into d by kb t. Okay. This has to be a constant. Okay, this has to be a constant, okay, because there is only one dimensionless group, right. So, for this problem this has to be a constant. What that means is that dB is equal to a constant into kb t by ud. I am sorry, d. Okay. Constant we cannot calculate from dimensional analysis, we have to do something more to calculate this constant. It turns out that a more exact calculation shows that this dB is equal to kb t by 3 pi mu d. Okay. It is called the Stokes-Einstein relation. Okay, so, that is the relation for the Brownian diffusion coefficient. Okay. So, using dimensional analysis we have found out an expression for the Brownian diffusion coefficient. Let us solve another problem. Okay. We take a particle with angular velocity omega rotating in a fluid of density rho, viscosity mu, and the particle diameter is d. Okay. And I want to find out what is the torque on the particle. Okay, I want to find out what is the torque on the particle. Okay. So, therefore, the dependent dimensionless group is the torque, okay, T. The torque has dimensions of force times distance. Okay. So, the dimension of this is force ml t power minus 2 times length, which gives us an ml square. Okay. Okay. So, the torque is ml square t power minus 2, and the independent groups are angular velocity, omega, which has dimensions of t inverse. Note that the angular velocity is the ratio of the linear velocity and the distance to the center of rotation. Okay. Linear velocity is L t inverse divided by distance is t inverse. Okay. The diameter d with distance with dimension L, okay, and then the fluid properties density rho with dimensions m L power minus 3 and viscosity mu with dimension m L inverse T inverse. Okay. So, those are the dependent and the independent dimensionless groups. Once again, the torque has a mass dimension, can be scaled by either the mass in density or the mass in the viscosity. You can choose either of those two to scale it. Okay. So, I will define a dimensionless torque. So, we have a total of 1 dependent and 4 independent quantities, 3 dimensions. So, there should be 1 independent and 1 dependent dimensionless group. Okay. The dependent dimensionless group contains the torque and other quantities. It contains the dependent quantity that can be scaled either by density or viscosity. Okay. In this particular case, I will scale it with the viscosity. Okay. So, I will define this as T into mu power alpha d power beta, okay, omega power gamma. Okay. Dimensions on the left and right side. Okay. M power 0, L power 0, T power 0 is equal to m L square T power minus 2 power alpha L power beta T inverse power gamma. Okay. And then write down the coefficients of the different dimensions. The mass dimension, right, I have 0 is equal to 1 plus alpha, length dimension 0 is equal to 2 minus alpha plus beta, and the time dimension 0 is equal to minus 2 minus alpha minus gamma. Okay. And you can solve these 3 quite easily. You will get alpha is equal to minus 1, put that in the equation for length and you will get beta is equal to minus 3, and put that into the dimension for time and you will get gamma is equal to minus 1. Okay. Therefore, T star is equal to T by mu d cubed omega. Okay. That is the scaled torque. Okay. Mu d cubed omega is the scaled torque. Okay. That is the dependent dimensionless group. There is also an independent dimensionless group. Okay. You can of course solve it the same way, right. Take the independent dimensionless group as rho times mu power alpha d power beta and omega power gamma. Okay. And then do the calculation, and I will just give you the total the result in the end. Okay. This is equal to rho omega d square by mu. This is the Reynolds number for the rotational motion of the particle. Okay. This is the Reynolds number of the rotational motion of the particle. Therefore, T star is equal to some function of Re. That is the relationship between the scaled torque and the ratio of inertial and viscous effects. Once again, if you are in the limit of low Reynolds number, density is no longer a parameter, and therefore, this dimensionless group has to be a constant. Okay. If you are in the limit of low Reynolds number, density is no longer a parameter, and this dimensionless group has to be a constant, which means that the torque has to be equal to a constant into mu d cubed omega, okay, for a particle rotating in a fluid. Dimensional analysis does not tell us what that constant is, but we can derive that constant from more detailed calculations. It turns out that that constant is just equal to pi, okay, and the expression is pi mu d cubed omega, yeah, okay, pi mu d cubed omega is the torque, okay, in the particle. Okay. A slightly more complicated expression, okay, torque on a charged particle. Okay. Rotating in a magnetic field. Okay. Here the independent dimensionless group, I am sorry, the dependent dimensionless group is the torque with dimensions m L square t power minus 2 as we had just calculated. What are the independent dimensionless groups? Okay. So, if I have a particle with charges on it, okay, rotating with some angular velocity omega in a magnetic field with a magnetic flux intensity B, okay, there is a torque exerted on the particle due to in the direction perpendicular to the angular velocity and perpendicular to the magnetic field, okay, in the direction perpendicular to the plane containing these two. Magnetic field is characterized by the magnetic flux intensity B. Okay. The charge on the particle is what is called Q. Okay. The total charge on the particle is what is called Q. Okay. And therefore, the independent groups, okay, one is of course the diameter with dimension length. Okay. Then there is the charge, okay, Q. Charge is current into time. So, the dimension is A times t. Okay. And the magnetic flux density, B. Okay. I leave this to you to calculate. Okay. It turns out that the dimension of this, the magnetic flux density, is m t power minus 2 A inverse. Okay. And then of course, you have the angular velocity with dimension t inverse. Okay. So, in this problem I have one dependent and 4 independent dimensionless groups. Okay. I have one dependent and 4 independent dimensionless groups, and these have a total of 4 dimensions: mass, length, time and current. Therefore, there is only one dimensionless group, okay, and that is going to be equal to the scale torque. Okay. One dependent dimensionless group, that is equal to the scale torque, and I can write this as T into Q power alpha, B power beta, omega power gamma and d power delta. Okay. So, this is the expression for the torque. Okay. So, once again m power 0, L power 0, T power 0, now amperes power 0, okay, because there is a current dimension here. It is going to be equal to m L square T power minus 2 into current, charge is current times time per alpha. Okay. Magnetic field intensity is m t power minus 2 A inverse per beta times T inverse per gamma and L per delta. Okay. And then once again I equalize, m 0 is equal to 1 plus beta, length dimension 0 is equal to 2 plus delta, okay. Time dimension 0 is equal to minus 2 plus alpha minus 2 beta minus gamma, and the current dimension, okay, 0 is equal to alpha minus beta. And you can solve these to get alpha is equal to beta is equal to minus 1, gamma is equal to minus 1 and delta is equal to minus 2. Therefore, the scale torque is T star is equal to T divided by Q B omega d square. Okay, so, that is the scale torque. Therefore, the torque has to be proportional to this product. Okay, this implies that the torque is equal to some constant into Q B omega d square. Okay, so, that is the expression for the torque. For a particle of charge q rotating in a magnetic field of magnetic field intensity B, okay, with angular velocity omega and diameter d. So, this gives you the use of dimensional analysis for determining the relationship between dependent and independent dimensionless groups. So, the next lecture we will start using this for transport processes. Okay. So, we will start using this to study transport processes starting with mass transfer from a particle. We will use dimensional analysis. Okay. I will continue this in the next lecture. I will see you then.